session of Climate Finance and Innovative Business Model. We will be delving into Unit 1, which is Overview of Climate Systems and Risk Assessment. This unit will be taken through by Dr. Benjamin Lamti, who has already joined into the session. Just to confirm if colleagues can hear me.
Yes.
Yes, we can.
Yes.
Okay, perfect. So for this unit, we'll have it today and Friday. Without taking much time, I'll just hand it over to Benjamin.
Okay. Okay, so good afternoon, everyone. Can you hear me? Yes, please.
Good afternoon, Doc.
Oh, okay. So the unit today is overview of the climate systems and risk assessment. Anyway, I think that I don't know whether we should do an introduction because we can see each other. But basically, I'll take you through this module. But I told David that I'm traveling on Friday, so you should make it Thursday, and he confirmed that it's Thursday. Isaac, you announced that it's Friday. It's not Friday. I'm traveling back to Ghana from Netherlands on Friday. So I told David, he said it has been arranged for Thursday, the second class. So let's get on for today's class. Now, I think I will share these notes with you guys after. Basically, the climate system, as we all know it, has components. I hope you can see the notes. Yes.
Yes.
You can see the notes.
Yes, we can.
So you have it. You have it later. It has components, and the components, as you know, I'm sure many of you know that, are the atmosphere, the oceans, the cryosphere, which is the component that has to do with ice, land. Land is both biosphere and geosphere. These are the major components. There's life on land, there's life in the ocean, so that's biosphere. But the major component is what we have mentioned. And the thing is that the processes in the atmosphere, for example, are at a different time scale compared to processes in the ocean, for example. So I have a component there, one of the subsections which are called time scales, right? The processes in the atmosphere are faster than the processes in the ocean. And there's a reason for that. This class, you are not
recording in progress.
You are not meteorologists, but there's a reason for that. We can look at the physics behind why that is happening. But then that's not the focus of this course. Then we have the issue of the cryosphere. The main impact of the cryosphere is what we call albedo. Albedo is reflection coefficient. Reflection coefficient. You see, the main source of energy in the climate system is the sun. I hope most of you know that. And the way the sun behaves is that when the radiation is coming from the sun, it passes through the atmosphere and hits the surface. So the Earth's atmosphere is transparent to solar radiation. So the solar radiation does not hit the air directly. It goes through the air and gets to the surface. So if the surface is land, the land absorbs the heat. If the surface is ocean, the ocean absorbs the heat. And then the surface will in turn heat up the air, which is in contact with that surface. You see how it works? So if you have ice on the surface, what happens is that the radiation is reflected. Most of the radiation is reflected back to space. And that is the impact that the ice causes. And the ice, we can talk of different ice. I have it in the notes, so don't worry. This is just listen to me. we can talk of different types of ice, right? So we have what we call seasonal snow cover, the one which comes on land, but we have sea ice. Then we have the ice sheets like Greenland and other things. These are all in the notes. Even on mountains, on some mountains, we have ice, right? They are called mountain glaciers. And basically, the key thing to know about ice is the albedo. They disrupt the radiation balance because of the albedo. But the other processes are there, which when you read the notes, you'll see. And then like time scales, I've told you already that the processes in the atmosphere are faster than the processes in the ocean. But the processes in the atmosphere influence the ocean and causes a change. And that change influences the atmosphere back. So we already get variability in the system, in the climate system, just by interaction of the various components. It's called internal variability. That already is happening before you can think about greenhouse gas or whatever. This is already happening. The interaction among the components of the climate system is already giving you some variability.
Professor Benjamin.
Yeah.
Yeah, sorry to cut you. One of the participants is saying the slides are not visible. Not easily visible.
Can I?
Yeah, maybe
I
if you
should
could
make it bigger. Okay.
Yep.
Let's see. Can I use percentage? You can just increase the percentage scale.
You can zoom. The button can zoom in. Take photo.
Is it better now?
Yes.
Yeah.
Yeah, it's better now. Okay. Okay. Sorry about that. And feel free to stop me. Feel free to stop me when you don't understand anything. Stop me and let me explain it. Okay? Don't wait till the end. You can stop me anytime. Now, where was I? So the time scales, bear in mind, it's very, very important. The time scales are very, very important. The processes proceed on certain time scales, and those things are important. In physics terms, we will say that these processes we are talking about involve what we call exchange of heat, momentum, and the moisture, for example. These are very important things in the climate system. These exchanges, if you know how it is happening, the source and the destination, the time scales, you can interpret many things if you know these things. For example, when the ocean is heated up, we all know that there's evaporation. That evaporation is not only water escaping, but it generates what is called latent heat. And latent heat is different from sensible heat. And their partitioning is important for many processes. But I will not go into the physics of these things. So just have an idea. I think when you read the notes, you will see all this, some of these examples there, right? Now, the predictability of the climate system. You see, there are what we call chaotic systems, and most of the processes are chaotic, but there are stable elements. You know, people have been asking questions like, if you cannot get the weather prediction 100% accurate, how can you talk about forecasting climate? Before I go there, let me ask a question. How many of you know about the different types of forecasts which the Met Services gives? Do you know about nowcasting? There's no. Maybe I should put that there as well. I don't think I have it.
No.
Do you know? But you know about weather forecast, right?
Yes.
Yeah. You know about? Do you know about seasonal forecast?
Yes.
Yes.
You know about seasonal forecast?
Yes.
Okay. So let's even pick just these two: weather forecasts, seasonal forecasts, and then you also know about climate change, right?
Yes.
Yes.
Okay, very good. Let me pick that. Let me just use these ones, the ones you know. But there are more. There are more. There's what we call nowcasting. There's what we call nowcasting, which is short range. It's like weather forecast for the short range, like 6 hours. That's called nowcasting. It's very important for some sectors. And then you can have a weather forecast, which is the one you know. That can be for 24 hours. It can be for 72 hours. It can even be for 1 week. That's the weather forecast. But we also have what we call sub-seasonal prediction, which can be for 2 weeks to 1 month. And then we come to the seasonal forecast. And in the seasonal forecast, we give 3 months forecast, but you update it every month. In Africa, we don't do the decadal climate prediction very much. We don't do it. So let me jump straight to climate change projection. The climate change information you get are not forecasts. They are not predictions. They are called projections. To get that clear, if anybody needs further explanation, tell me. I will stop and explain further. I don't want to confuse you. And I know most of you don't have the physics background. So when you need any explanation, just stop me. I will explain.
Sorry, Benjamin.
Yeah.
I think it would be nice to have a short explanation. Just a brief one.
Okay. On which one? The climate projection?
Yes, the projection.
Oh, let me even explain both prediction and projection. Let me do that. You see, in meteorology, we have what we call initial conditions. Number one, let me step back. Most of the information we get at this scale are obtained from models. What do we mean by models? These are mathematical models. And what do they do? The physical concepts, the processes we are talking about here now, they are physics. So they are physical concepts. They have been formulated in terms of differential equations, mathematical. And then that formulation is what is the model. So when you hear climate model is just a numerical model, like weather model, climate model. They are numerical models. What do we mean? They are differential equations. The physics of the weather systems have been expressed as differential equations, and they are being solved. Now, the models are trying to mimic the globe, the Earth, but they can't do it perfectly. So they use what is called grids. I can, if need be, I can incorporate it in the notes before I give you. I can put something there. They use what is called grids. They take the globe and they divide it into grids. And they assume that each grid is a continuum. So when you get temperature for a particular grid, it's assuming that in the whole grid, the temperature is 1. You should understand this when you are interpreting climate model output. That's what they are assuming. Now, the whole of Ghana can maybe only 2 grids can fall over the whole of Ghana or Kenya or Mali or anywhere. And that is the problem with models. I mean, it's not a problem, but you have to understand it when you are interpreting, because they give very useful information. So coming from that background, the models are used for weather forecast. Now, the weather forecast is different from what we call numerical weather prediction. I just explained the numerical aspect to you. Numerical weather prediction is the information coming out of the weather model. That's numerical weather prediction. But the weather forecast uses that information together with other types of information, like satellite data, like different sources of information. Even the forecaster uses his own knowledge, local knowledge about the place. All those things, you put them together before you can get a weather forecast. So what the model is giving you is not what you give to the public. That's the prediction. That's the numerical prediction. What the mathematics of the physics has given you. But you have to, sometimes the model, if it's not realistic, you, the weather forecaster, must know. And then know how to interpret what you are getting from the model. Okay? So that's for weather prediction. Now, when you come to, and in weather prediction, what you do is you get initial values, you feed it into the model, and you tell the model the time step, what we call time step, like if it is 1 o'clock now, you tell the model whether you need information for the next 1 hour. You specify all this in the model before you run it. And it will generate 1 hour interval data for you, output. If you want the information for 30 minutes, you tell the model. So that is what is called prediction. You give information to the mathematical system, and it can tell you what will happen in the next time step. That's what happens for weather. When you come to climate change, it's not the same. Because the weather is very short term. Many things don't change. If you give the information now and you want it for the next step, many things don't change. Many things remain constant. The atmosphere, pollution, whatever within 1 hour will not change drastically. The human beings, activities that are being carried out by human beings will not change drastically. So you assume all those things to be constant and you rely on the mathematics of the physics systems. But when you come to climate change, so many things are happening. So you can't do the same thing. You do this one, but in addition to this, you have to take into consideration how the energy consumption has changed over time, how human industries are producing and with their effect on the climate, how even human activities like farmers and all those things. So many things come in addition to the simple mathematics we did for the weather. You have to bring them together. And then based on that, you can say that what the climate of the future will be. That is why with climate change, we don't call it prediction. We call it projection. Many assumptions are made. These things, you don't know them. They are in the future. So you assume that the way people are consuming electricity now will not change. Or it will change. If it will change, by how much? The way people, the farmers are cultivating their land now, will it change or not? If it will change, how will it change? To what extent will it change? You have to make all these assumptions and put it in the model. And then you come up with a future climate. So whilst we call the weather a prediction, the weather one we call it prediction, the climate change one we call it projection, because more assumptions are being made, right? Well, in terms of, if some of you have physics background, with the weather one, the initial values you give it, we call it initial conditions. But with the climate change one, we call them boundary conditions. The initial conditions are not enough. We call them boundary conditions. You have to feed it with information from other components of the climate system together with the information of what I just explained. So the climate change, they are called climate change projections. Whilst the weather, the output from the weather model is called numerical weather prediction. They are predictions. Any questions?
Is it possible for you to come back on the boundary something?
The boundary conditions?
And just explain,
and the initial
please.
conditions. And the initial conditions, right?
Yes.
Okay. So the initial conditions, you have a mathematical equation. You feed it with some values at a given time, t equals 1. And you solve those for t equals 2. You solve those equations for t equals 2. So all what the equations need is what we call initial conditions, the initial values you give to them. So assumption about energy consumption, farmer activities, whatever you can think about, they don't come in here. And that's how we do the weather prediction. That's how the weather models run. They have the information in there, but the way they use them is different from the climate change prediction. Because in a very short time, in 1 hour, the farmers don't change. Not many farmers will change their production so drastically in 1 hour. So the information is in the model, but the way the model uses it is completely different if you are considering very long time periods like climate change. That's why with the climate change, we call it boundary conditions. In addition to this, you say give it these initial conditions, but you also have to give it more information, and those ones are called boundary conditions. The boundary conditions are more important than the initial conditions in terms of climate change. So the boundary, you see, the atmosphere is a subsystem, the ocean is a subsystem, land is a subsystem, and you need information from all of them to interact. In addition to external forcing, whatever human beings are doing, whatever industries are doing, whatever, all that information come in, and then you make assumptions. Somebody's hand is up.
Yeah, I have a question.
Okay.
On the side of projections, because weather is, or climate rather, is such a fragile variable to work with, wouldn't long-term projections be filled with anomalies going forward?
Okay.
And then wouldn't that make the model not all that great?
Okay. Now, you use the word anomaly. And anomaly has a special meaning. What you want to say is uncertainty.
Yeah.
The models definitely have uncertainty. Definitely. They have uncertainty. And that is why it is important to understand the model output and how to use it. And when you are going to make decisions, you take the uncertainty into consideration. So the models have uncertainty, but it doesn't make them useless. It's a matter of understanding the uncertainty in the information and how to use that uncertainty together with the information the model is giving you. These same models are those that give us the information we are using now about climate change. All this noise about climate change, the information is mainly from models. It's mainly from models that we are able to say that by 2020 it will be like this, by 2030 it's mainly from models. But you have to understand the physics of the system. You have to understand the information coming out and how to interpret that information, and how do you use the uncertainty in the model, in the information you are getting from the model. You have to have this understanding, and then you will see that the models are useful. They are not perfect, but they are useful. Okay, Derima, your hand is up.
Thank you very much, sir. The explanations have been very, very lucid, but something came to mind while you were talking about the boundary conditions. Now, in your statement, you said that in climate change projections, that boundary conditions are much more important than initial conditions. But what came to mind was, are we looking at the planetary boundary system that is used to measure climate change impact when we're talking about boundary condition? Is that what we're looking at? These whole planetary boundaries and all that they use in evaluating the various impacts of climate change on various spheres and all that. So I want to understand, are the boundary conditions the same thing as the whole planetary boundary stuff that the scientific community uses? I don't know if my question is clear.
I will try to break it down, and you tell me whether that's what you mean.
Okay, sir.
The planetary conditions you are talking about, when you say planet, the Earth is a planet, right? And right now, we are talking about one planet, the Earth. Are you getting it? The boundary conditions is for the model, but it is the model trying to use information from the Earth. Are you getting it?
Yes, sir.
There is a model which is trying to mimic the Earth, and it needs some information to be able to mimic the Earth and give you useful information. And one of the things it needs is the boundary conditions. That is, it's a modeling term. Let me put it that way. That's what I want to say. It's a modeling term. Some information is termed the boundary condition. You see, in the Earth, we have what we call the planetary boundary layer. The Earth itself is divided into layers. But this boundary condition we are talking about is mathematical, is referring to the model. I told you the model we are talking about is a mathematical model, right?
Nous parlons du modèle mathématique.
I told you that the model we are talking about is a mathematical model, right?
Je vous ai dit que le modèle que nous utilisons, c'est un modèle mathématique.
So, the boundary condition has to do with the model. Even though the model is about the Earth, the planet, which is only the Earth, which is the planet we are dealing with now. So we talk about the Earth.
La planète Terre.
We talk about the Earth's atmosphere, which is the realistic thing.
On parle de l'atmosphère de la Terre.
Somebody is not muted. Salome, mute yourself. So, do you get it now?
Yes, sir. So, to get it clear, the boundary conditions are purely mathematical.
They are mathematical things, yeah.
Yeah. So, is it possible for you to maybe itemize one or two of those boundary conditions, because we're just hearing boundary conditions?
Yeah.
Maybe like a variable, or like a variable you can give us a claim name. Maybe let's say like soil moisture, or maybe all those kind of variables that can be measured.
Okay. So they are actually variables. For example, the initial conditions when you do modeling.
Par exemple, les conditions initiales.
Right.
Lorsque vous faites le modèle,
temperature is one.
So there's a lot of noise from the background.
Yeah.
I think it's interrupting a lot. Yeah.
Isaac, can you mute everybody so that only the person talking can?
The interpreter, Salome, you might have clicked English, not French.
I was disconnected. I was disconnected. Let me. I'm trying to re-enter the meeting.
Okay, so we are talking about meteorological variables here. And by meteorological variables, I'm sure you know them. Temperature is one of them, right? Pressure is another one. Are you following? Wind is another one. So the variables, if you want to mention variables, these are some of them.
Can you reassign me, please? Please reassign me. Isaac.
Okay, I'm reassigning you.
So Derima, do you get it now?
Yes, sir. Yeah, thank you very much.
If you want variables, then we are talking about meteorological variables.
Have you reassigned me?
Temperature, pressure, wind, those ones. But it's not all the meteorological variables that you give to the model. It doesn't need all of them. For example, it doesn't need rainfall. The model computes the rainfall from these parameters you give to it. So you understand it now?
Yes, sir. Thank you.
Okay. I move into modeling. Okay. Now, I know everybody is interested in climate change, but it's very, very important to understand that everything is not about climate change. You see, I always say this. The climate change projections give us information, right? For example, one common information which is standing out in all the IPCC reports is that the intensity, duration, and frequency of extreme events will increase in the future. I think most of you know this, right? Have you heard this statement?
Yes, sir.
Very good.
Yes,
So
sir.
when you say the intensity, the duration, and the frequency of extreme events will increase in the future, that's a projection. That is a projection. So heavy rainfall is an extreme event. Heat wave is an extreme event. What you are telling me is that the rain, let's take rain alone. Simple, everybody will understand rain. If in my area, the way I'm getting heavy rainfall now, you are telling me that it will be more frequent than that, and the rainfall will even be more intense than that, and the duration will even be longer than that. That's what that statement means. Now, if right now, you see, when that time comes, the rainfall will no longer be a climate projection because it will be real, it will be happening at that time, right? So it will happen as a weather event. That projection they gave, when the time comes for it to materialize, to happen, it will happen as a weather event. Many people overlook that aspect. They are just interested in the policy. They get this information and they use it to formulate policy. But it's very, very important to understand that those climate change information you are getting and using, when they actually happen in real life, will happen as weather events. So it is very, very important to understand the weather systems. It's very important to build the weather infrastructure. We should be able to predict or forecast what is happening now and improve the forecasting infrastructure in such a way that if the rainfall increases, becomes more frequent than it is now, the weather infrastructure should be able to capture it. If it will be, because the information must be given to the public that, hey, now the rainfall, previously you were getting it once every week. Now it's going to be 3 times a week. You have to be able to capture that information. Or the duration over this particular area, it rains for just 1 or 2 hours. But from the changes that have happened in the climate system, now we can get rainfall continuously for 6 hours. To be able to do that means your forecasting infrastructure must be improved enough to be able to handle the changes which are being projected. So what is weather and what is climate? That's what I put here. That's our next thing. Can somebody tell me what is weather?
I think weather refers to the short-term changes in biological components, while climate refers to the long-term changes in meteorological components. So if you're looking at weather in terms of rainfall, you're looking at the short term, while if you're looking at climate in terms of rainfall, you're looking at the long term, which is usually over 30, 35 years thereabout. I think that's the little I can remember.
Very good. But you see, you left out one word. You use long term, that is good. But people use the word average. Whether a climate is more or less average. And we all did basic mathematics, right? When you say average, you know what it means, right?
Sure.
When you say average, we know that we are talking about mean, right? Average is the same as mean, right? And
Yes, sir.
The mistake we make most often, the reason why I brought this up is that it's not only about the mean, it's also about the variability. For example, let's take Kenya now. I'm sure most of you are in Kenya, or Mali, wherever you are. You can know the temperature right now, right? You can even know the weather right now. But assuming somebody, a friend of yours, is outside Mali or Kenya, wherever you are, and he wants to visit you, he wants to have an idea about how the weather systems in Mali behave. The information you are going to give to that person is climate. You are going to tell that person that in January, most of the time, or generally speaking, in the month of January, Mali is very dry and cold. That is not weather, that is climate. How did you get that information? And if the person is coming in, let's say, July, you are going to tell the person in the month of July, normally it rains a lot in Mali. That is our major rainy season. How did you get that information? You have observed, the weather has been observed for so many years, like some of the first guy said, about 30 years, and you have taken an average and have arrived at that conclusion that this is the average conditions, which is the climate of July. And this is the climate of January for a given place. That's the difference between. But having said that, so we say that climate is what you expect, but weather is what you get. Having said that, we also know that the rainy season for this year can be different from the rainy season for next year. We all know that, right? That is variability.
Yes.
That is variability. So it is important to also include the variability when you are talking about the averages. I have it in the notes. You can see it. I have it in the notes. Now, the next question I want to ask you is, what do you mean by season? These are basic things, terminologies. People use it by heart. It just occurred to me to make it foundation. Then we can talk. We can add on to it. What do you mean by season? Can somebody answer that?
Can you say it's a period? Because it's a time when a particular, like you said, probably weather is expected.
Yeah, maybe you can say it's a period in which a particular climate occurs.
Okay. So the second person has used the climate to link to the season. But you see, has used the type of weather to link to the season. The first person who spoke just said it's a period. So everybody knows when we say winter, right?
Yeah.
We talk about winter, we talk about summer, we talk about spring, and we talk about autumn. These are seasons. But bear in mind that season is linked to the calendar year. When you talk about that season, it is linked to the calendar year. So you have to even specify, are you talking about the Northern Hemisphere or are you talking about the Southern Hemisphere? Normally, if you don't qualify it and you say winter, everybody assumes Northern Hemisphere. So if you are not talking about the Northern Hemisphere, you have to add the Southern Hemisphere winter. Are you getting the difference? Now, the winter occurs within some calendar months, December, January, February. Then the spring occurs within March, April, May. Then summer comes, I'm talking of Northern Hemisphere, June, July, August. And then autumn comes September, October, November. This is the Northern Hemisphere one. But it is opposite in the Southern Hemisphere. It is opposite in the Southern Hemisphere. You must be clear in your mind about this one. Then now let's put that one down. Let's take the second person. The second person said it is a period within which a particular type of weather occurs. So in Africa, most of the time, let's even use any part of Africa, we talk about rainy season and dry season, right? In some parts, we even talk about Harmattan season. The Harmattan season is actually the dry season. But that doesn't tell you, when you say rainy season, it doesn't tell you which month of the year you are referring to. Like when you say winter. When you say winter, automatically you don't have to, if it's not hemisphere winter, you don't have to mention any month. But if you tell me the rainy season, I'm going to ask you, when is the rainy season? When? So let's say if you are in Mali and you are talking about the rainy season, I'll say, so when is the rainy season? And when is the dry season? Then now you are going to tell me the rainy season is June, July, August. And the dry season is from after August. So you are not telling me the months. So let's say in West Africa, for example, the heaviest rainfall, in most places, there are 2 rainy seasons in West Africa. I think Kenya, you have more than, East Africa, you have more than 2. But West Africa is mainly 2. And the major one is during the Northern Hemisphere summer. That's the monsoon rains. So it is even called the summer monsoon, West African summer monsoon. The major dry season in West Africa is the Harmattan time, which is the Northern Hemisphere winter period. That's when you have the Harmattan. December, January, February. West Africa, the Harmattan in West Africa. See, that's so it's Northern Hemisphere winter. That's when you have that. But you also say dry season. So much as you are using the season as per the calendar year, you can also use it for weather events. That, like the second person answered, must be clear in your mind, right? Okay. Now the next terminology I want to look at, I think I've mentioned it a bit, but now we need to make the difference clear. What we call climate variability. You can have the variability which is from year to year. Like I gave you an example. The way the rains will behave this year may be different from the way the rains behaved last year, and it can also be different from the way the rains will behave next year. So that is year to year variability. It is called interannual variability. But you can also have even within the rainy season, within the given year, you can have the rainy season behaving in a weird manner. That is called intraseasonal variability. Within the season, there is variability in the season. That's called intraseasonal variability. You want to know when there will be dry spells. You want to know when there will be wet spells. You know, and if you think you know it, this year you have observed a certain trend, next year is behaving differently. That within season variability is called intraseasonal variability. And then the one which happens from year to year is called interannual variability. And you can even have decadal variability. There are 10-year cycles, which also vary. So you can even have decadal variability. All these are not climate change. We haven't reached climate change as yet. All these are not climate change, but they are very important for many sectors. Agriculture, water resources, energy, all these are very important for everybody. Because you have to understand the variability, and then you have to be able to know what is associated with variability and what is associated with climate change. It's very important to know the difference. So all what I'm describing now is just variability. We have not reached climate change. Any questions? Any questions before I continue? So I can move on, right?
No, for now, yes.
Okay. Okay.
Yes, I can.
Now.
So far, so good.
Okay. Now, there was something I wanted to put in the notes, but because your background and the emphasis of the course, I left it out. So I'm going to try and explain it. If you don't understand it and you want me to put in the notes, I will put it. Now, I want to talk about climate change. And you see, there are some terminologies associated with climate change. How many of you have heard about greenhouse gas?
I have, sir.
Everybody.
Yes.
Have you heard about greenhouse effect?
Yes, sir.
Agriculturists would definitely know
Yes, sir.
about greenhouse effect. What about the non-agriculturists? Now, so we are going to talk about, and then
Maybe geologists.
geologists also know about greenhouse effect. So the terms I'm going to talk about now, we are going to talk about the greenhouse effect. We are going to talk about greenhouse gases will come in definitely when we talk about the greenhouse effect. We are going to talk about global warming. Before we talk about climate change, it's very important to know these things. It's very, very important to know these things. Okay? Now, let's start from the greenhouse effect. The greenhouse effect is actually a term which was borrowed from agriculture. In agriculture, they have what they call glass houses, right? And that glass houses, I don't know how many of you are agriculturists, but those glass houses, what they do is that they allow a certain type of radiation to enter, but they prevent certain type from escaping. So they keep it in the system. So the agriculturists, they can plant things in the glass houses. Now, let's bring it to the atmosphere. So we are going to talk about the greenhouse effect of the atmosphere. You can talk about greenhouse effect of clouds, greenhouse effect of even water vapor. But we are going to talk about the greenhouse effect of the atmosphere. I told you that the sun's radiation is the source of energy. Most of the energy on the earth, for the processes on the earth, comes from the sun's radiation. And when that journey starts, the radiation goes through the atmosphere. The Earth's atmosphere is transparent to the sun's radiation. So the sun's radiation, which is also called short wave radiation, is short compared to some other type of waves. It goes through the atmosphere easily, and then it gets to the surface. And the surface absorbs that heat, whether it is land, whether it is a water body, it absorbs the heat. Now, air is in contact with that surface. So when the surface absorbs the heat, after a certain time, it begins to re-emit heat. But the heat which is being re-emitted by the surface is a different type of heat. It's a different type of radiation from the radiation which came from the sun. The radiation which came from the sun, like I said, is called shortwave radiation. But the radiation which is re-emitted from the Earth's surface, whether from the water body or from the land, is long-wave radiation. So that is long-wave radiation, infrared. Whilst the one from the sun is short-wave radiation, also ultraviolet. These are all physics things, which I just want you to pick the simple terms. We are saying that the Earth's atmosphere is transparent. It allows the radiation from the sun to pass through it and arrive at the Earth's surface. But the radiation from the Earth's surface, which is a long-wave radiation, is prevented from escaping into space so easily like the way the short-wave radiation came. So the Earth's atmosphere traps the long-wave radiation. So it allowed the short-wave radiation. Where did the short-wave radiation come from? From the sun. And where did it arrive at? The Earth. So the Earth, after absorbing that short-wave radiation, will now re-emit another type of radiation. It doesn't emit the same shortwave radiation. It transforms it into another type of radiation because of some things which happen when it absorbs the shortwave to re-emit what is called long-wave radiation, infrared radiation. But that infrared radiation, the atmosphere, the Earth's atmosphere, is not transparent to that long-wave radiation. So it absorbs that long-wave radiation, the atmosphere. And then the atmosphere on its own begins to also emit radiations in all directions, going up, coming down, every direction. Now, what is the composition of the Earth's atmosphere? Who can tell me? What is the composition of the Earth's atmosphere?
Different coffee. Nitrogen.
Say that again.
Gases like nitrogen, carbon.
Very good. Very good. Gases like nitrogen, carbon, oxygen, methane, nitric oxide, they are all there. Aerosols, water vapor, they are all there in the atmosphere. That's the composition of the atmosphere. Water vapor is there. It's a very important component. Which means that long wave, which is prevented from escaping, has been absorbed by these substances. You get it now? And then these substances in turn re-emit the long wave in different directions. Some goes to outer space, some comes back to the Earth's surface. And that is how the Earth's surface where we live is warm enough for human beings to live there. If the Earth's atmosphere were not opaque, were not preventing the long-wave radiation from escaping completely and to go into outer space, the Earth will be too cold for us to live here. It will be too cold for us to live here. But because the atmosphere doesn't allow all the long-wave radiation from the Earth's surface to escape into outer space, and it keeps some, it absorbs them and re-emits some of them back to the surface, the heat is normal, it's reasonable enough for human beings to live on the Earth. Now, this is what is called. Yeah. Okay. Ask questions.
Yes. I guess I don't have. I'm not. My background is in sociology.
Mm-hmm.
So let me ask this. So now, if let's say the amount of heat that is trapped by the atmosphere that comes from the Earth,
mm-hmm.
and then is
re-emitted,
directed to the Earth, is what causes the warming.
Yes.
Okay. I came across some explanation. I want to find out if it is right.
Mm-hmm.
What I understood from that explanation was that the amount of heat that comes from the atmosphere,
mm-hmm.
For example, if the atmosphere releases heat,
mm-hmm.
and then is absorbed by the Earth,
yeah,
maybe the amount that comes from the atmosphere
mm-hmm.
is less.
Mm-hmm.
And then the amount that comes from the Earth
mm-hmm.
is more, then you have the issue of this warming that we are talking about, or heat we are talking about. But when you have a situation where more comes in from the atmosphere, but less is released back, then we would have no issue of this warming and then the heat that we are talking about. I don't know if that is right.
Okay, you are going into the physics of it. Let me tell you. You see, we have values. We have values for how much is incident on the Earth's surface and how much leaves the Earth's surface. There are values for them. and there is a balance. It's called the radiation balance. So that radiation balance can be offset, and that's what you are talking about. But I am trying to not take you into the quantitative aspect. I'm trying to talk about greenhouse effect. And then from greenhouse effect, now I've been able to I will tell you about the greenhouse gases. Then I'll talk about global warming without talking about the radiation balance. What you have mentioned is what is called the radiation balance. And I can give you a diagram. I don't know whether I have it. No, I didn't give it to you. I can give you a diagram of what you are saying. But the heating is not just dependent on those values. Because it also depends on where you are. Right? So so the heating it's what I'm describing is the general form that somebody's hand is up. I'm coming, I'll give you the chance. Let me finish with this one, then I'll give you the chance. Generally speaking, this in physics we even calculate how much temperature it would have been. Generally speaking, the heating we are talking about here is not extraordinary heating. It's about heat, comfortable heat, which makes life comfortable for human beings. Now, let me very good. Something came to my mind. Have you woken up in the morning and then on a cement or platform or even on grass, you find dew? Have you seen that before? Have you seen dew?
Yes.
Dew on yeah. Do you know how it comes about? The radiation from the surface in the night, when there's no more sunshine, the radiation from the surface is now escaping. So, like the gentleman said, there is no sunshine, so there is no heat coming in from the sun. So the heat that is from the surface is now escaping. And if the heat that is escaping is happening at a rate which is faster than what the atmosphere is bringing back, like the gentleman said, the surface will cool. And when the cooling is very extensive, it will condense the air which is in contact with that surface. And when you condense the air, what do you get? You get liquid. That's the dew we see in the morning. It's called radiational cooling. It's because of radiational cooling. That is the dew we see in the mornings. So you don't see that dew every day. I'm trying to explain the gentleman's case to him. You don't see that dew every day because that type of the heat coming from the atmosphere and the heat leaving the surface, it's not constant. It's not always the same. So on days when you have the heat leaving the surface to be more than the heat which the atmosphere is returning back to the surface, you see the dew. You see the cooling. You get it now? So we are talking about different time scales here now. What?
Yeah, if I miss it. So the earth cools every day. So if this dew that is emitted from the eye, if we not see it every day, so what causes it? Is it transit?
Yeah, that's what I explained. I'm saying that the gentleman's question was, there is heat escaping from the surface of the earth, and there is heat coming from the atmosphere back to the surface of the earth. In the night, I'm using night because the sun is gone.
Yeah.
And I'm saying that if the heat leaving the earth is more than the heat which the atmosphere is sending back to the earth, you will get a cooling effect.
Yeah.
And that cooling will, if it is strong enough, will cool the air. The air will not only be cooled, but it can even condense it, which is the liquid, which is the dew we see on the surface in the morning. Yeah. So we have to be cautious about the time scales. The gentleman's question is more on daily time scale. The greenhouse effect is, we are not talking about daily time scale here. We are talking about climate time scale. Are you getting it?
Yeah.
Good. Now somebody's hand is up. Before I continue.
Okay. So like for this is like West Africa, we have 2 seasons. We have the rainy and the dry season.
Yeah.
So during the rainy season, we will not experience such because there's a huge downpour of rainfall. So the earth will at its own space. So it's only during the dry season we will experience that dew.
Yeah. Mostly it's during dry season. It's mostly during dry season. Yeah.
Okay.
Good. Now,
maybe
all this plenty talking that we have done, the solar radiation or shortwave radiation from the sun passing through the atmosphere, arriving at the surface of the atmosphere absorbing it and re-emitting long-wave radiation back to the atmosphere, and the atmosphere preventing that long-wave radiation from escaping. So the atmosphere is discriminating. When it is short-wave radiation, it allows it to go through it smoothly, fast, get to the surface. When it's long-wave radiation, it doesn't allow it to escape easily like that. It absorbs it and it re-emits it, right? That property of the atmosphere is the atmosphere which is behaving that way. That property of the atmosphere is what you call the greenhouse effect of the atmosphere. You get it now? That property of the atmosphere is what you call the greenhouse effect of the atmosphere. And what we have just described now is the natural greenhouse effect. No human influence. Everything is business as usual. Things are happening every normal the way we expect them. That's the natural greenhouse effect.
So,
any questions about that? Mm-hmm.
Yeah, so you spoke about infrared and so you are saying that the process through which these through which these processes take place is what we call the greenhouse effect.
Very good. The processes where the shortwave radiation is allowed to go through the atmosphere and arrive at the surface of the earth, but the long wave radiation from the surface of the earth is prevented by the same atmosphere from escaping into outer space. That is called the greenhouse effect of the atmosphere.
Mm-hmm. Sorry to jump in. My hand was up before and it was not picked. So my question is on, this is very fascinating for me. I'm also not from geography background, so this is really interesting. So now my question is around, you see, when sometimes during winter, there is, I want you to explain to me that there is sometimes the sun is out, there is sun, but it's still cold. But there is sunshine, but it's cold. Why are these differences when sometimes in summer the sun is out and it's hot? So why are these differences in these times? What changes in the greenhouse effect? Maybe that's my question around during these two times.
Okay. So your question is similar to the gentleman who asked about, who said he read something which says that when the heat coming from the atmosphere is more than the heat coming from the surface, then we get heating. That's similar to your question. Now, the greenhouse effect is on climate timescales. It's not on daily timescale we are talking about. It's on climate timescales. It's over a period of time. What you are asking now can happen on daily timescales. Like today, you can have the sun shining, but it is cold.
You undo.
So in that case, we are not talking about the greenhouse effect there, right? Even though it's happening, but we are not talking about it there. We are looking at the factors which is affecting that day. We are looking at the factors which is affecting that day. It means that there's some cold air mass coming from somewhere. So even though the sun is shining I told you the radiation from the sun doesn't heat the air. It does not heat up the air. The radiation from the sun goes straight to the surface. And after the surface has absorbed the radiation from the sun, it is the surface which will now heat the air. But if the sun is shining and the surface has absorbed that sun's radiation, the shortwave radiation, but there is a cold air mass from another source, you will not feel the heat. You will feel the cold air mass. So on a daily time scales, things happen which we average all of them out when we are talking about climate time scale. So some of the questions you people are asking now are what happens on a particular day. That's weather. You are now asking about weather questions. But the greenhouse effect, we talk about it when we are talking about climate. So the example you just gave today, it can be the sun can be out and you can be feeling cold. Tomorrow it will not happen. The sun can be out and you can be feeling hot. All this is weather. All this you put all of them together, average them out, and then you come up with the climate.
Oh, okay. So, but the climate remains the same. So we can say even. Okay. That is why I mentioned variability. I don't want you to only think about the average, because normally that's what we say. Climate is the average of weather. But it is not only average. It is average and variability of weather.
As I mentioned.
Okay. Now, I'm going to ask you a question. What is natural greenhouse effect of the atmosphere?
Professor.
At least make sure that you are grabbing it. What is the natural greenhouse effect of the atmosphere? That's what we have done so far. That's where we have stopped so far. I've not added anything. I want to add, but I want to make sure. Yeah, Derima.
Okay. From what you've explained and from the little I've read, greenhouse effect is the ability of greenhouse gases to trap and retain outgoing radiation from the Earth's surface. So what happens after the trap is that they act like a thermal blanket, trapping and then warming the environment. Something like
Very
that.
good. But you have left out something. You didn't say that they allow solar radiation to pass through them. You spoke about one side of it.
Okay.
Yeah. Next person. I want somebody to do. Yeah. Firar.
Thank you. I think it is the natural atmosphere that surrounds the Earth that capture the sun radiation or the light from the sun, and then the Earth atmosphere, just like a blanket, condense it and then make it almost suitable for Earth's living things.
No, it does not capture the radiation from the sun. The atmosphere does not capture the radiation from the sun. It allows the radiation from the sun to go through, but it absorbs the radiation from the Earth, the surface. That ability is what is called the greenhouse effect. Ruben.
I was going to say the natural greenhouse effect is a situation when the atmosphere allows short waves to pass through into the Earth's surface, and also traps the long wave that are coming from the Earth's surface into the atmosphere and traps it to divert into the atmosphere.
Do you have a physics background?
I have a geography background.
Okay. Yeah. Okay. Because your answer captures it. Your answer is just the ending part, which you left something off. But the essence of, you gave the essence of the thing. The atmosphere allows the solar radiation or shortwave to pass through it and get to the surface of the earth, but it prevents the long wave radiation from the surface of the earth from escaping into outer space. It absorbs it and it re-emits it back, or it re-emits it in all directions into outer space and back to the surface. That is the natural greenhouse.
Yeah.
Now, I'm doing this step by step. You see, I didn't talk about the composition of the atmosphere when I just used the word atmosphere, right? But we have explained that the atmosphere contains gases, it contains water vapor, it contains aerosols, right? The gases are not the same. The gases have different chemical properties. So this thing we just described, there are some gases which within in the atmosphere which are responsible for what we just described. It's not all the gases which are causing it, what we just described. It's not all of them. There are some of them which cause what we just described. They are in the atmosphere together with other gases, but they are responsible for what we just described. And those gases are called the greenhouse gases. Can you give me an example?
Yes, I can give you.
Yeah.
Carbon dioxide, methane, nitrous oxide.
Yeah.
The sulfuric chloride, hyperfluorocarbons.
Very good. It's enough. It's enough. It's enough. I don't know whether I should put some in the notes. Maybe I should put. I didn't want to. This is too much physics, so I didn't want to. But yeah, that's it. You have given examples.
It will help some of us.
Sorry?
I said it will help those of us who don't have a.
Oh, okay. So I can put
science background. Yes.
I can put. You see, I didn't want to make the notes plenty so that the reading will be boring. But I can put it, no problem. I've been teaching this. I can put that one. So examples of the greenhouse gases.
I've typed some of them in the chat box as well.
Okay. Okay. So people can look at it. The key ones, the three. When you are mentioning, if you can't mention many at all, you should mention at least three. And he did all of them: nitrous oxide, methane, and carbon dioxide. These three, they are very important. The key ones. So these are greenhouse gases.
Water vapor and ozone.
Sorry?
I said water vapor and ozone.
Yeah. Water vapor too is important. But I said key because there is physics behind all what we are saying, which we are not going to do. So I'm trying to keep it simple. Water vapor is important. Even CFCs, he mentioned fluorocarbons. They are important. All those ones. And even ozone to some extent, yes. Oxone to some extent. But there is not all type of ozone. You have to be careful. Some ozone is good and some ozone is bad. All that, there's physics behind them. Okay. So we have described the natural greenhouse effect. Now, and we have also described or mentioned greenhouse gases. And we have said that the greenhouse gases are responsible for the natural greenhouse effect. I think this one is a simple message. Everybody gets that summary, right? If somebody doesn't understand it, you can raise your hand because you need to understand that before we move to the next explanation. The greenhouse gases are responsible for the atmosphere discriminating between the short wave radiation from the sun and the long wave radiation from the earth's surface. The greenhouse gases are responsible for that. Those in the atmosphere are responsible for that. So the greenhouse effect is attributed to the greenhouse gas. That's why they are called greenhouse gases. The effect is called greenhouse effect. And the gases which cause this greenhouse effect are called greenhouse gases. Very simple, right?
Yeah, so please, if it will not bother you, could you just give a brief summary of the greenhouse gas effect again?
Okay.
A brief summary, yeah.
Okay. So when we see the greenhouse effect, we mean the natural greenhouse effect. The natural one is what we are describing. All what we have been talking about is only the natural greenhouse effect. What is it? It is the ability of the Earth's atmosphere. When you are describing it, don't use gases. Don't mention any gas.
Okay.
Finish the description. Then when you want to say anything about gases, you can add it. If you add gases, you confuse yourself. Just use atmosphere. Okay? So